Okay, let's talk some more about linear dynamical systems. I'm going to review what we talked about last time quickly and fill in a few details which I skipped. Let me remind you, we're doing sections 9.1 to 9.3, and I'm going to be jumping around a little bit. So let's recall where we were. We were talking about, we had a vector-valued function, so f was a map from R to Rn, and we were usually taking n to be 2, so let's say 2. And we have a 2 by 2 matrix, and we're interested in the differential equation f prime is equal to a f. And I'm going to say it explicitly now, something which I sort of implied last time, which is the following. The set of solutions is a two-dimensional vector space. And so what does that mean? That means we can find two solutions, u1, I think that's a vector valued function u1, and another vector valued function u2, which are a basis, in other words, so that every solution is of the form C1U1 plus C2U2. I should put the here, C1U1 of t plus C2U2 of t for some C1 and C2. So I did a bunch of examples that last time that worked this way, and I'm just saying this is a general fact. There's always two linearly independent solutions, and such that every solution is a linear combination of the two of them. And we've talked about this a number of times over the course of the semester. This is a great example of an abstract vector space. This vector space that I'm talking about here, this two-dimensional vector space, where does it live? Where are the vectors? Well, this if I call it V, then V is a two-dimensional space of functions. So there's this giant infinite dimensional vector space floating around somewhere, and this is a two-dimensional subspace of it. And those two vectors are in there and their sums. And the key point about this is that this equation being linear and homogeneous says that the solutions is a vector space. The key point is if let me use new names here. If G1 of t and G2 of t are solutions, so is G1 plus G2 and a constant times either one of them. And I showed that last time in our examples. It's because this is a linear operator. And so, for example, what is G1 plus G2 prime? Well, that's G1 prime plus G2 prime. And since G1 is a solution, G1 prime is equal to AG1, and G2 prime is equal to AG2, and then you can factor this out to get AG1 plus G2. And so if G1 is a solution and G2 is a solution, then G1 plus G2 is a solution. So that shows that this thing is a vector space. And the fact that it's two-dimensional, well, that takes a little bit more work, and I'm not going to I might say a word about that next time, but for now, let's just leave it at that. Okay, here's another aspect of this which I alluded to last time. So we have this equation f prime is equal to a f, and the general solution is C1 U1 of t plus C2 U2 of t. And the second key thing, closely related to what I just said before, is suppose I give you any point. Take any point in the plane, x naught, y naught. Then there is a unique solution, f of t, which goes through that point, and you might as well have it go through the point at 0. So that is to say, f of 0 is equal to this point. And I'll say another aspect of this. So let me call this 1. And then second of all, the curves that you get this way, the trajectories, I'll call them, trajectories don't cross. So that's a little bit vague, but I think you know what I mean, and anyway, I'll remind you. So let's just draw a little picture over here. So if you give me a point, then there's a unique solution which goes through that point. And this is the curve f of t, which is the solution there. And if I picked a different point, I'd get a different curve. And these curves never intersect. And the reason that they don't intersect, well, it's really from the first part. If they did intersect, if you had a point and you had a curve which went through it, and then you had a different curve which went through it, well, then that would violate this unique solution business, because this would be a solution f1 and this would be a solution f2. These would both be solutions satisfying f1 of 0 is equal to f2 of 0 is that point x0, y0. So this statement here, the business about there being a unique solution with a given, this is called an initial value. I should emphasize that. Specifying the point x naught, y naught is called specifying an initial value. And to say that the trajectories don't cross, well, that's more or less exactly what this first part is saying, the fact that there's always a unique solution going through a point. Okay. So both of those properties I illustrated in the examples I was doing last time, but I just wanted to make it clear they're very general properties. Okay, another thing that I talked about last time, which I'll remind you of, is the idea of a vector field. And this is quite a bit more general notion than the examples that we're doing, but that's okay. I'm going to focus on this kind of example. Suppose you had this f prime, and I'll put the t's in now. F prime of t is equal to a applied to f of t. Well, what you do is you draw this picture where at every point in the plane xy, you draw the vector a applied to xy. And what this equation is telling you is that at the solution that goes through this point, the change is a vector in this direction. You should think of it as being pushed in that direction. The derivative is the tangent. And so that says that the solution curve is tangent. This is tangent to the solution curve. And so if you were to plot all of these vectors, it gives you a very good idea of what the solution looks like. And let's do a couple of examples of that. I'll explain them in a little more detail. I did a few last time, but let's do a few more. Let's look at an example I mentioned briefly last time in class. Let's take A to be this matrix. So what do these vector fields look like? let's just plot a couple of sample points. So for example, at the point 1, 0, if you apply this to 1, 0, you get 0 minus 1. So here you have the vector pointing down like that. And at 0, 1, you get, when you apply A to this, you get 1, 0. So you get this here. And let's look at 1, 1. You get 1 minus 1. And so that's when you're at 1, 1, that's this point here. It looks like that. And I mentioned this last time. In this example, the trajectories are circles. Isn't that a beautiful circle? And these guys are all pointing like this. Okay, well, let's jump over to Mathematica and get a decent looking drawing of this stuff. So what I've done here is I've plotted the vector field in that example from the previous slide. You can see, for example, that along this positive x-axis, for example, all of the arrows are pointing straight down. And then as you go around over here, they're all pointing to the left. And here they're pointing up. And here they're pointing directly to the right. And also you see that as you move away from the origin, they're getting longer. Now, the length of the vectors doesn't matter so much for the curve, but it does tell you something about the motion. We'll talk about that a little bit later. In any event, and down here are the trajectories, and they didn't come out very well. I'm not sure why. I'll have to fiddle with Mathematica and make it look better, but you can see that somehow there are some circles here. So let's look at another example. Okay, well, I've jumped to another example here. I've taken the matrix 2 minus 1. You all know its eigenvalues are 2 and minus 1. That's what I'm being told here. And the eigenvectors are 1, 0, and 0, 1. And this is the vector field. And you can see it's going out along the x-axis, and the arrows are pointing in along the y-axis. And here is the corresponding here are the corresponding trajectories. Let's see. Here are the corresponding trajectories. So this was basically the example. This is essentially the same as the example I did in class. In fact, it's even easier because I took a diagonal matrix. And you can see that the trajectories are asymptotic to the x-axis here and asymptotic to the y-axis here. And similarly in each of the 4 quadrants. Okay, well, rather than try and do more of these on the slides, I will just do some more examples like this in class with Mathematica. So I'll see you then.